I'm going to turn it over to Alan, let him introduce himself and get going with the program. And thank you very much, everybody.
Righty. Well, good evening, everybody. I think everybody's in the, at least in evening time here. I don't know if we've got anybody from overseas or not. But, my name is Alan Wolke. I'm W2AEW. I'm actually the technical coordinator for the Northern New Jersey chapter of the ARRL field organization. And the talk we're going to go through tonight is talking about vector network analyzers and specifically the NanoVNA. Let me make this kind of full screen. You should all be able to see that. Other thing I'll mention in addition to that view, if you mouse over to the upper right corner, under the view, in addition to being able to see gallery or speaker view, there is kind of a, I forget what it says, something like side by side. So for example, if the little images of the people attending or myself are overlapping the slides, if you select the side by side option, it will them to not overlap, so nothing will get obscured in what you're looking at. So anyway, we're going to have a little chat about the NanoVNA. Little shameless plug for my YouTube channel down here at the bottom of the screen, just youtube.com/mycallsign. Well, 300 some odd videos up on the channel, about 100,000 subscribers and about 17 million views of some of the videos on my channel, everything from radio to basic electronics to test and measurement to things like that. So hopefully a little something for everybody. Sounds like a winner to me. So let's get moving on and chat about VNAs and the NanoVNA. Just taking a look at this. Why do we want to talk about this? Why do we want to bring the topic up? Introducing the new is that there's these ridiculously inexpensive NanoVNA products that are out there now that make vector network analyzers accessible to hobbyists like us. It's something that traditionally outside the realm of possibility for most hams, but it's not anymore, so it makes sense to talk about them. Is chat about what a vector analyzer is in the first place. What is it good for? What can we actually do with it? And then we'll take a look more closely at the NanoVNA itself and learn more about what we can do with this little platform. So with that, let's get started. So the first thing is, what is a VNA? Right? And we kind of mentioned earlier, VNA is a vector network analyzer. That probably doesn't really help answer the question of what it is. So if you turn to everybody's favorite search engine, Google or something like that, to get a definition of a vector network analyzer, you probably get something like this. It's an instrument that measures the magnitude and phase of the reflection and transmission properties of the ports of a device versus frequency. Now, I know that doesn't really help you either. Okay? It doesn't really kind of clear things up. So let's kind of break it down. It's simple for everybody to get a better intuitive feel for what a VNA is. So first, there's a number of professional VNAs out there, because that's typically where most VNAs are used, kind of out in the world. And there's three pictured here, one from Tektronix up at the top, one from Copper Mountain here in the middle, and then kind of a very high-end device from Keysight here, a 4-port device. VNA it's an instrument that's used to characterize RF devices. And we'll go into more detail about what types of devices and what type of characterization as we move on here. And generally, they used to only be used by RF engineers in a professional environment due to cost. So professional units can cost thousands of dollars or more. This unit on the top is about a $10,000 unit. This Copper Mountain one, $6,000 or $7,000, and this top of the line kind of 4-channel Keysight PNAX is over $238,000. So most of us don't have that kind of scratch to spend on an instrument for our hobbies. So a $50 VNA sounds pretty darn good. With VNAs, there's a ton of acronyms and terminology that is kind of using VNAs, or that is typically used just by RF engineers. But if you're doing any research in terms of how to use a VNA, you're going to come across these things. So it makes sense to talk about and define what some of these acronyms and terminology is so that you're comfortable with using a NanoVNA. So the first one is something called the DUT. Now, what is a DUT? The DUT simply stands for the device under test. And that could be an antenna, it could be a filter, it could be a piece of coax, whatever it is that you're testing, that's your DUT. They'll typically have at least one port, maybe two. It might not be something that's got two ports. It might just be an antenna, for example, that has one port. It might be an amplifier or a filter or a hunk of coax, which essentially has two ports.
Alan, can I interrupt for a second?
Certainly.
Your audio is pretty choppy. I don't know why, but you're breaking up.
All right, well, let's do this. Let me change the audio device that I'm using here and see if this helps. Let me change, hold on a minute, just give me a second. Let's see, open speaker and
microphone. So let me see, how is that better?
Yeah, I believe it is better. Yes.
Okay, all right, so we'll use the headset here. Okay.
All right, thank you.
All right. No problem. Well, thanks for letting me know. So that's I'm glad we straightened that out. Hopefully this will be better. So any DUT, device under test, is going to affect the signal being applied to it and going through it. The input impedance of the device is going to affect the applied signal, okay, in one way, shape, or form, especially if it's not impedance matched to the source and the feed line. And as we all kind of learned through even our basic electronics, if you want to get maximum power transfer from any kind of a source to any kind of a load, you want the impedances to match. In reality, really, what we learn about is matching the source and load resistance. The reality is you want the complex conjugate match. We're not going to talk too much about this. It's a topic for a whole nother video. But understanding the complex impedance of a device is oftentimes very important when we're either doing design work or impedance matching or something like that. And this is part of what a VNA can do for you. So another thing that's kind of important when we start talking about VNAs and talking about RF signals in general is rather than talk about signals in terms of voltage and current, it's often more instructive to talk about them as waves and talk about their magnitude and phase. So the magnitude obviously being the amplitude of the signal. The way to think of phase, because phase is something that can confuse a lot of people. One way to think of phase is just a delay or an offset in time between two signals. You can see these two signals here at the top. Let me put a little pointer on screen here. These two signals here at the top, differ in magnitude, and they differ in their position in time, or in a sense, they differ in phase. It looks like by about 90 degrees. Okay, figuring you've got 360 degrees per cycle. This thing's shifted over about a quarter cycle, so it's about a 90-degree phase shift. Okay, this little animated graphic here is kind of simulating if I was being able to stretch out a transmission line between a source and a load. We can see that the applied signal can get reflected off a load and reflect back as the red signal here. And the position of those two, the phase of those two, varies depending on the length of that line. So a lot of ways to think about phase, but I just kind of want to give you some pictures in your mind so you can see what we're talking about. So as I mentioned, if we have a source is going to be used to apply a signal to our device under test. Okay. Now, of course, if it's a two-port device, some of that signal is going to go through that device. And those are what are called the transmission properties of the DUT. Okay, it might be a filter, so it might have a passband characteristic or something like that. It might be a coax, it just has some loss versus frequency. But that's the transmission properties of the device. And a VNA can be used to measure that. And of course, if there's an impedance mismatch between the source and the transmission line and the DUT input port, there can be some signal reflected off of that port back towards the source. And those are called the reflection properties of the DUT. So the device reflection and transmission properties will alter the magnitude and phase of the applied signal from the source. And fundamentally, that is what a VNA measures, is the magnitude and phase of the transmitted and reflected signal with respect to the signal that was applied by the source. So before I go on, just real quick, I'll stop and pause see if there's any questions. I can't see the chat, so someone who's looking at that might have to let me know, or if you've got a quick question, you could pop off mute real quick and ask me. If not, we'll continue. All right, let's continue on. So this is a block diagram of a very basic VNA, in fact, very similar to what is in the little NanoVNA we're going to be talking about. So essentially inside the green box is the VNA. You essentially have an RF source that supplies a signal to, through a port to the device under test. And then we've got a number of receivers and splitters and things like that in here. So these directional couplers, or sometimes bridges, in the case of the NanoVNA, it's a bridge, but in many VNAs, it's a directional coupler, are used to pick off a piece of the signal that's going in the forward direction towards the DUT, and that's being measured up here. And then also any signal that's reflected off of the DUT and comes back down the line is picked off and sensed by this directional coupler, okay? And then all of these signals, the reference signal, if you will, that's being applied, the reflected signal coming back, and the transmitted signal going through the DUT are all measured in these receivers, and they're commonly called the R, or reference receiver. The A and B receivers will measure the reflected energy and the transmitted energy. Okay, so these receivers essentially measure the magnitude and phase of the forward, reflected, and transmitted signals. And then all those results from those receivers are collected and computed inside a computer or microcontroller inside the VNA to display results in various formats. Quite simply, that's what a VNA does. And we're going to talk about those formats that we display in. Some of them will be very familiar to you in terms of things like SWR versus frequency. Other measurements that can be made might be something that you haven't come across, maybe things like S parameters, or a plot on a Smith chart, or return loss, or something like that. Okay, but at the end of the day, they're all just different terminologies for the same type of a thing. So the transmission properties, again, are based on this ratio of the signal measured in the B receiver compared to the reference receiver. So we're sending out a signal, we know what that reference is, the B receiver is what's being transmitted. So that ratio, B over R, is essentially the transmission properties of the device. What does this output look like compared to what was applied at the input? So that could be looking at something like gain or loss through that device. It could be looking at an S parameter called S21. It's also called the transmission coefficient. We'll talk about what that is and define that for you. And then also could be looking at the insertion phase or group delay through a device. Okay. Similarly, any measurements or any signal being reflected off of the DUT input port and coming back into, in this case, port 1, will be sensed and measured by the A receiver. So that now the measurements that are based on A with respect to R, okay, the A versus R measurements are going to be things like we can compute, things like VSWR, voltage standing wave ratio, versus frequency, or a reflection coefficient, or S11. Again, we'll define that here in a moment. Or measure things like return loss, or even calculate the input impedance of the device. So these are very common things that you can do with a VNA. You certainly don't have to do them all. You might get a VNA and only use it to measure SWR. That's fine. You can certainly do that. A $50 NanoVNA is cheaper than most antenna analyzers you can find out on the market today. Now, most professional vector network analyzers will have this source and these couplers and receivers on both ports. So you can measure transmission and reflection in both directions. The NanoVNA we're going to talk about here does not have that. It only has got the source on one side. So it's actually called, the terminology for it is a two-port, one-path VNA. where most professional VNAs are at least 2-port 2-path, and sometimes more than 2 ports. Okay. So from that simple block diagram, let's look at what a VNA is good for. If we consider just single port measurements, again, these are going to be reflection-based measurements. And obviously, the one that we probably will use most often is looking at the SWR of an antenna or antenna system. Okay, that's a very, very simple and common task to use a VNA. But you can also use it to measure the complex impedance of an antenna system, a filter, other things like that. Okay. It can also be used to even measure components, resistors, inductors, capacitors at a particular frequency of interest, okay, to ensure that any of the parasitics associated with these devices can be measured and characterized as well. You can characterize things like crystals and filters and things like that as well. Now, with some additional processing within the instrument itself, you can actually even measure feed line length or a distance to fault in a feed line. By measuring essentially the frequency response and then looking at where you get some peaks and nulls due to that discontinuity in the feed line. So you can use that to compute what the length is, or even like a distance to fault. I mean, let's say you've got an antenna up on a tower and all of a sudden things aren't working so well. You can actually run this distance to fault test to kind of see if you've got a break or a short or an open or something like that in your feed line partway up the tower without having to go climb the tower. Of course, you'll have to go up to fix it, but at least you'll know how high you have to climb. When you're making 2-port measurements, then again, these are the transmission measurements. This could be like, for example, if you've got a bandpass filter that you might use during field day, you might want to check its insertion loss or check its band stop characteristics outside of the bands of interest using a VNA. You can also use it to measure loss in a feed line versus frequency, or the delay that is present in a device under test, or things like amplifier gain and frequency response. Okay, if you got an LNA or something like that, you can characterize that. Okay. So what this means is that you can use a VNA to characterize everything from antennas to duplexers, filters, inductors, caps, amplifier splitters, balance, chokes, all these things that we typically use as hams can be characterized and the performance measured using a VNA. So one of the terminologies that we looked at a slide or two ago was S parameters, S21, S11. And again, for folks that are not in the RF industry, the terminology of S parameters can be a scary thing. So let's take some of the mystery out of what an S parameter is for you. Now, S parameters are called, they're called S parameters because they stand for scattering parameters. And again, I know that doesn't help you define that again. So, so let's go define that a little more clearly. So the S parameters is simply, again, it's a ratio of a measured response to a stimulus. And the numbers here refer to the port numbers. So in this case, SXY means that it's the response measured at port X as a result of the signal being applied to port Y. Okay, so if we take a look at, for example, S11, that is the response measured at port 1 in response to the signal being applied by port 1. Okay, so it's again just the reflection off of the DUT port. It's just another way of looking at essentially what's called the reflection coefficient, and that can be computed as an S parameter called S11 or reflection coefficient. Can also be mathematically manipulated into SWR. Okay, so S11 is effectively an SWR type measurement or reflection measurement. Similarly, S21, okay, is going to be the response through the DUT. The response measured in the B receiver from port 2. Okay, so that's where the 2 comes from. So we measure at port 2 in response to the signal being applied at port 1. So it's the B over R measurement. It's the through response through a device, S21. And these are the 2 most common S parameters that you would measure with a VNA. And the S parameters are complex quantities, meaning that they have both a magnitude and phase. Because anytime there's any reactance involved, either in the input impedance or any delay through the device, there's going to be a phase shift potentially, and that is part of that S parameter. So you're measuring both a magnitude and a phase. Oftentimes we only care about looking at the magnitude. We don't really care what the phase is. The only time we typically care about that is if we're looking to measure, to compute the complex impedance, and maybe to use that to develop, say, a matching network for an antenna or something like that. Okay, but quite simply, that's all S parameters are, again, is these ratios, and you can figure out whether it's a reflection measurement, a forward gain or loss measurement, or maybe a output reflection measurement, or a reverse transmission measurement, whether it's S11, S21, S12, or S22. Okay, but that's all S parameters are. So another thing that can be confusing when people talk about VNAs is the fact that, well, the VNAs come with this calibration kit. I've got to run this calibration called a user calibration. Why do I have to do that? I mean, I pick up my MFJ antenna analyzer. I don't have to calibrate it. I just use it. Why isn't it just calibrated at the factory? Okay. Well, the reason for that is there's a number of things that a factory cal can't take care of. So why do we actually need to run a user cal? So first thing is that the VNAs generally can measure a fairly large dynamic range, meaning that, let's say you're measuring a filter, for example, ideally you want the filter to have, 0 dB of loss in the passband, and you want it to have, tons of loss, okay, at the stop bands, right? So it might be, maybe you want the stop band to be, 60 dB down compared to the through characteristic. That's a 60 dB dynamic range. That's a factor of 1,000,000 to 1, okay? So what that means is that any little nonlinearities or issues in the analyzer itself or due to the setup can affect the ability to make those very large dynamic range measurements. So part of the calibration is to measure any of those imperfections and remove them from our measurement. So another piece of it is because we need to measure phase, we need to do a calibration. Because remember what I said phase was? Another way to think about phase is that it's a measure of delay. So the longer transmission line you have, or a piece of coax you have between the instrument and your device, the more phase delay you're going to have. But for example, if you want to make a measurement at the input port of your device, you still have to connect it up to the VNA. So the VNA doesn't know how that interconnect is, how long that interconnect is. So you can't predict what the phase would be at your DUT. So by doing a proper user calibration, you can establish what we call a measurement plane, so that the phase is essentially normalized right to the connection points of the device under test. And so all the phase and delay associated with the interconnect getting to your device can be calibrated out. Okay, so again, that's also part of what happens when you do a user calibration. So a factory calibration can't account for these things because it doesn't know what you're connecting up to, how you're connecting up to it, what you want included in the measurement, and what you want excluded or calibrated out of the measurement. So a factory calibration can't do any of that. This is why we need to do a user calibration. So, but when do we need to do that user cal? Really, it's whenever there's a configuration change. Maybe I'm changing cables, or I'm changing adapters or fixtures of how I'm connecting up to my device. Or more importantly, and probably the most common reason, is when you have a new frequency range that you're measuring over. You set up a frequency range, you do a calibration. You set up to a different frequency range to make a measurement. It's ideal to do a repeat of a calibration over that new frequency range. Was there a question? I heard someone pop in there for a sec. Okay, so I
No,
think we're
go
good.
ahead.
Okay, so so this is why there is this process of doing a user cal. It's actually something very easy to do. Scares a lot of people off, but there's no reason to. It's actually something pretty simple to do. So we're gonna I'll show you what that looks like. Okay. So again, the user calibration corrects for what we call these systematic error sources. So things like tracking error. Tracking error refers to the source and receiver frequency response. So the frequency response of the source, of these couplers, of the receivers and things like that, they're going to have their own little bit, frequency response. So part of the calibration removes that, it measures that, and therefore can remove it from the measurements themselves. Another systematic error source is the source and load mismatch errors. Okay, at the ports themselves, so that can actually be accounted for in case the impedance at these ports isn't a perfect impedance match to your DUT or to the 50 ohm coax, for example. So that can be measured and removed. And also things like directivity and crosstalk. Directivity is a measure of these couplers in terms of how well they reject the signal going in the other direction, right? So for example, this coupler here, we only want to sense the signal going in the forward direction, but there is going to be some small amount of signal that's coming from the other direction that's going to couple to that port as well. And so that's called the directivity of the coupler. So we want to be able to measure that and account for that. And similarly, crosstalk. If there's any way that a signal gets from one port to the other, bypassing your DUT, we can call that crosstalk. And we want to be able to measure that and remove that from our measurement as well. And then finally, any of the cables that we've applied to the ports of the DUT or ports of the VNA to get to our DUT, we want to remove those so that we establish our measurement plane right at the interfaces to our DUT. So all of these things are things that are computed and then removed from the actual measurements when we're making a measurement on a DUT. And this is part of what the user calibration does. So what are some of the common display formats? What are we going to display? What are the formats of that? So the most common measurements, with any of the VNAs are measurements that are made versus frequency sweeps of one way, shape, or form. So one of the more common ones is the reflection coefficient, or S11. And oftentimes all we're really interested in is looking at the log magnitude of that. So we make that measurement and do a logarithmic conversion to give you that number in dB. The reflection coefficient is typically a number that varies between 0 and 1. Okay, 0 meaning I'm getting no reflection, or 1 meaning that all the signals being reflected back. And we're just doing a log magnitude of that. There is a phase associated with that, and that can be measured as well. But the most common thing is a log magnitude of S11. Similarly, we can mathematically convert that into SWR, and that's going to be in a linear type thing. So like 1.3 to 1, 1.7 to 1, 2.5 to 1, etc. That'll just be a linear ratio. If we're looking at complex impedance, looking into maybe an antenna or something like that, that's often plotted on a Smith chart. Again, talking about the Smith chart could be a whole nother talk that we could do at some point in the future. I've got a nice talk prepared on that and a number of videos on that as well on my YouTube channel. The transmission coefficient, much like the reflection coefficient, is typically displayed as log magnitude and potentially phase. But then insertion, phase, delay, etc. are generally shown as linear plots. And then there is a transform function that can take reflection measurements and transform them into time to do like a TDR, a time domain reflectometry type measurement to measure things like distance to fault or length of a piece of coax or something like that. And it basically is measuring the reflection coefficient, but then transforming it to time to kind of say, what kind of a delay till I get some reflection back. And that's typically measured in time. And it's often helpful to change it from log magnitude to linear, because you get a little bit of a sharper peak in the result. Instead of getting a kind of a soft, compressed, logarithmic peak, you'll get kind of a sharp linear peak there. So when you're doing a transform measurement, it's often helpful to use linear instead of log mag. So those are some of the common display formats that you'll get on the VNA. So with that, let's go take a look at the NanoVNA and what it is. Okay. Now the NanoVNA itself was developed. The initial project was developed a couple years ago, probably about 4 years ago, and was a project that was kind of put up on like a public domain site, and people started playing around with designs and things like that. And a couple of developers picked up on it and started kind of mass producing things, or at least making it a lot of design files available. So a lot of people picked it up and started mass producing it. So unlike, the antenna analyzers you can buy from the likes of MFJ or Rig Expert or something like that, there isn't one company behind the NanoVNA. So that kind of makes it a little confusing when you go out to look for one, because like, well, you don't just go out to buy one from that manufacturer or this manufacturer. There are different manufacturers and different design variants that are out there. So you've got to start doing your homework a little bit. The original unit had just a small 2.8-inch diagonal display. It actually didn't even have the plastic case that I see on this one here. It was just kind of a stack of boards kind of bolted together with a couple of connectors sitting outside. And the original is often called the H version because it's the initial of one of the developers that originally put it together. There's an H4 version that came out, which is essentially basically the same RF hardware, but with a 4-inch display. And typically the VH4s were all available with a nice molded case, and that's the one that I've got right here, is the NanoVNA H4, kind of what I based this talk around. Okay. A pretty nice unit. The 4-inch display for anybody who's over 40 years old is really helpful compared to the 2.8-inch display on the original one. There's also another variant called the NanoVNA-F, also has a 4-inch display. That one is actually in an aluminum case instead of a plastic case. And there's a couple of additional little changes to the firmware that I thought were actually pretty nice, but it's also cost about double the money of a NanoVNA H4. Okay, so, but that's another variant that's out there. And then that was kind of the initial generation of the NanoVNAs, were kind of variants on those guys. Several of the original developers and some other folks got together and started developing what's called the V2, or kind of the next generation of VNAs, and given this very unfortunate name of SAA2, okay, like signal or scalar analyzer or something. I'm not sure what the SAA even stood for, but it's called SAA2. People often refer to it as the V2. It goes a bit higher up in frequency. Again, initially offered without a case, kind of like this picture right here. Okay, but then, even just over the last few months, we're starting to see other variants of this with different size displays, some in cases, some without, some with N connectors, some with SMA connectors. But so I would say as of fall 2020, I still kind of like the NanoVNA H4. It's a stable design. There's not a lot of people mucking around with it anymore, and you can get the pretty good reliable supply for it, get good support for it. There's a number of folks that have developed some interesting variations of the firmware to give you some interesting capability. It's only about $60. It's pretty easy to get. In the US, a really good source for this that we'll go into later on is R&L Electronics. So I still like the H4. This SAA2, or again called the NanoVNA V2, does have better performance than the H4. Initially with a 2.8-inch display, but now we're starting to see availability of 4-inch display models with different types of connectors and things like that. And the SAA2, the guys who are developing the stuff are actually developing improved performance even over this guy here. The most recent one that they've been talking about over the last couple of weeks goes by the name NanoVNA-V2 plus 4. Okay, so it's a V2 plus some enhancements with a 4-inch display. That's kind of where that comes from. So, but again, it's a little bit of a moving target with these things, because again, it's not a single manufacturer. But if you go to some of the websites I'll show to you a little bit later on, you can kind of get directed to find a pretty decent copy of these instruments, rather than some of the knockoff copies that are being produced by some of the folks in China and things like that. So, but that's kind of the state of where things are these days. So a couple more details on the NanoVNA. So generally all of them are, as I described earlier, 2-port, 1-path, meaning they've got a source only on one of the ports. They've got essentially 2 ports to measure both transmission and reflection properties. The H and the H4 units will cover from about 50 kilohertz up to 1.5 gigahertz. That's the unit I have here. Goes up to 1.5 gig. They do have essentially a built-in battery, so they can be operated standalone. They've got a USB port on them, so they can be connected up to a PC and used with some PC software that provides a number of advantages. Probably the foremost of which is to not have all the displays stacked on top of each other. You can actually have separate plots that are not all overlaid on top of each other, but also can do some improvements in terms of the number of points that are used in the sweep and things like that. So, you know, kind of the place to go to as your starting point for the NanoVNAs in terms of researching them and seeing what's out there and looking at the special interest groups that are out there and firmware files is just to go to nanovna.com. And that will kind of bring you to kind of a very simple little menu where you can get to a number of places. This last link here for the wiki and user group is essentially this link here. And from there, there's folders or places where there's firmware files and a lot of some user guides and a link to get onto the mailing list for these mailing lists that a lot of us are on these days. So that all can be found there as well. For the SAA2, I found there's two separate groups, kind of the official website that's kind of run by the designers of the SAA2 and are also working on these new improvements is this nanorfe.com. So that site right here. And then they've also got their own wiki and user group there as well. But again, we're going to focus a bit more on the H and the H4 in the rest of the presentation here. Because when I first put this together, the SAA2s weren't even out. So I just kind of added some of this stuff as we moved on here. But I think that for most of what we do as hams, the performance of the H4 for 55, 60 bucks is unbeatable because some of these SAA2s cost at least double that. This is what's under the hood. And I brought it up here not to critique or review the design, but just to kind of show that it's actually pretty simple. Okay, there's where channel 1 and channel 0 and channel 1. One unfortunate thing that the NanoVNA folks did compared to a professional VNA is the professional VNAs will generally call these ports port 1 and port 2, like I've been describing. Unfortunately, the NanoVNA folks call them channel 0 and channel 1. So it can be a little confusing. So port 1 is channel 0, port 2 is channel 1. Okay, so they still go in order, they just slipped by a digit here. So that's where the reflection measurements and source are provided on channel 0. The transmission measurements are measured on channel 1. The RF source is a little microcontroller controlled synthesizer. Anybody who's done any kind of homebrew work in the last couple of years might have run across this SI5351, just a little programmable RF source. There's a bridge that is used instead of the directional couplers to essentially determine the transmitted and reflected signal or the impedance mismatch at channel 0. There are 3 of our old friend, the SA612, or basically the later variant of the NA602 Gilbert cell mixers that are used to take the incident signal, the reflected signal, and the transmitted signal and mix them down actually into audio signals. And that's what's coming out of these mixers. Those audio signals are then applied to a very inexpensive stereo audio codec. These are chips that go into a lot of modern audio equipment, digital audio equipment, CD players, things like that. So they've got some high quality digitizers in them and a lot of digital signal processing. And because these are made by the billions, they are dirt cheap. So that's why it's inside this NanoVNA. All of this is controlled and by a little microcontroller that kind of controls the synthesizer and essentially the analog processing guts, if you will, of the NanoVNA. And then there's a display and voltage regulation, battery charging, and things like that. So this is the actual schematic of the H4. Again, just to show it all fits on one page. It's not very complex. I'm not going to kind of go through everything, but you can kind of see where all the bits and pieces are: the microcontroller, USB interface, the RF source, the mixers, and the audio codec. It's all right in there. So let's chat a little bit about the user interface of the NanoVNA. So right on the top of the NanoVNA is this little kind of rocking back and forth jog wheel. It can be rocked to one side or the other to do things like move markers back and forth or move up and down in the menus. And they can also be pushed to make selections. So it's a rock back and forth and a push type of a deal. The screen is a touch screen, so you can touch on the screen to make selections, things like that, and to touch on menus and numeric keypads and stuff. And you can also do like a tap and slide if I wanted to drag a marker back and forth on a trace. You can just put your finger on it and move it. So, and fairly simple menu structure. The home menu or the top menu generally looks like this, where you've got display functions, marker functions, stimulus functions, calibration functions, etc. And each of those will lead to other menus to kind of go through and set things up. And we're going to run through just a few of these in an example or two. Like the display menu allows you to select what traces are visible, what channels those traces are attached to, whether it's channel 0 or channel 1, meaning measuring reflection or transmission properties, what format and scaling you want to display it in. The stimulus menu, for example, allows you to set the start and stop frequency or a center and span to measure, so you can set up what frequency range you want to measure, etc. When you do calibrations, like I mentioned earlier, the user calibrations, there are memory slots where you can store that calibration so that you can recall it later. So if there's measurements that you make, reasonably often, maybe you're working on a design of a filter or you're working on an antenna, you always have a particular frequency range you want to make measurements over. You can run the calibration over that frequency range, save it into a slot so that anytime you want to repeat that measurement, you just recall that memory location and it's all set up and ready to go. You don't have to repeat the calibration. And then there's a USB port on this unit. It's right down here on the bottom. That allows you to charge the unit, the internal battery, as well as to use the PC-based software. So let's kind of walk through a little bit more details on the calibration, and this will kind of help us walk through some of the menu structures and stuff too. But I want to give you a couple of details on the calibration here. Again, kind of emphasizing why it's a bit important. Most of the VNAs, the NanoVNAs, only contain 101 points in the frequency sweep. So you might just say, well, I'll calibrate it from 1 megahertz to 450, and I'll never have to calibrate it again because that encompasses everything from VHF, UHF, and most of the VHF I'm going to use, right? The problem with that is that because it only has 101 points, you're only getting calibration over specifically at those points. So if I did a 400 megahertz span, right, I'm going to have calibration points every 4 megahertz. Well, that'll skip right over some ham bands. They're not 4 megahertz wide, right? So a lot of the VNAs will interpolate the calibration between the points, but that's not going to be as good as actually having calibration data at your points of interest. Okay, so again, by setting up the frequency range of interest and then getting essentially 101 measurement points over that frequency range is a much, much better way to go. Now I got a little asterisk here next to that 101 points, and that's because some later versions of firmware made by some other third parties will offer the capability of doing more than 101 points. Okay, but for the most part, out of the box with the firmware that comes from the manufacturer, you're going to have essentially 101 points. So again, the calibration may have a fairly coarse spacing, right, in terms of where the measurement points are. The span divided by 101 is what you get. So again, most of them will interpolate between the points, but it's always a good idea to calibrate over the frequency range of interest. So just some points to think about that. Again, the firmware I've got on my NanoVNA will do 401 points, but still that's not a whole lot, especially if you're measuring over a wide frequency range. So if you want to measure, say, a multi-band antenna, okay, that covers from 40 to 10 meters, you probably don't want to do a single cal between 7 megahertz and 30, okay, because you're still going to be a little bit too coarse. You're better off having multiple calibrations over those particular bands of interest to get a better result in each band. So as I said, and noting that firmware from other developers is one called Dislord. That's the one that I'm using on my instrument that give you up to 401 points in your measurement. So this is a couple more details of what that calibration looks like on the instrument itself. On the display, there's a little column of digits that appear on the left-hand edge. And the first line will show a capital C when the frequency range you've got set up is a calibrated frequency range, meaning that the calibration is loaded is valid over that particular range. If you got a calibration loaded, but it doesn't match the frequency range that you've got set up, it'll be a small letter C, which indicates that you're calibrated, but you're probably interpolating because the frequency range doesn't match. The number following that indicates the memory slot that calibration that you're using is stored in. Okay. One thing that's handy on the VNAs for most of them, if any calibration that you store in slot 0 gets recalled when you power the unit up. Okay, so it's kind of a default power up condition. These other letters, if you will, or digits, refer to directivity, reflection, and source match errors. Okay, so this says that you've done the calibration and these errors are now, and the error correction for those things are being applied. These generally all apply to channel 0. These are all applied to essentially reflection-based measurements. The T and the X stand for the transmission and crosstalk corrections being applied. So when you run through the full 2-port calibration, all of these letters will show up. Okay. This first set, the D, R, and S, are essentially the measurements that are made by applying the calibration standards to channel 0. That's required essentially for all your measurements. These latter two are only needed really when you're making through measurements, okay, using both ports. If you're only going to be making single port measurements, you don't really have to do that second half of the calibration. So this is the actual process of how you do it. And I just went through this just to kind of show you how you walk through menus as well. So if you bring up the main menu on the instrument, it looks like this. And we start by hitting the cal button. That brings up the calibration menu. And you start by resetting to clear the current calibration. Once you do the reset, this menu will still stay here, and then you hit the calibrate button. Once you hit calibrate, then it's going to prompt you to attach an open to channel 0. So there's a little open standard that comes with the instrument. You attach that, you hit open. Once you do that, then you'd apply the short and hit short, and then apply a load and hit load. So these 3 cal standards, a 50 ohm load, a short, and an open, are all part of what comes with the NanoVNA as the calibration kit. Okay. And those are the ones that will do that first channel 0 calibration, and again, required for all measurements. If you're going to be making 2-port measurements, then you also want to do the isolation and through measurements. For the isolation measurements, you leave the 2 ports disconnected or apply a load to channel 1 to kind of isolate it and shield it, if you will. And then the through measurement is just connecting a coax between channel 1 and channel 2. Once you've done the calibrations that you need, or run through these cal standards, you hit done, and then it'll bring up a menu to ask you to say which slot you want to save that calibration to. And if you select slot 0, again, that's the one that's recalled on power up. And ideally, you want to connect all of these cal standards at the location where your device would normally attach. Okay, and that would remove the phase and delay and the loss, if you will, of your interconnect and calibrate them out of your measurement. Okay. So another way to look at this is something called the calibration plane. Let's say this device is the thing we're measuring. Okay, I'd connect that up through a piece of coax here. When I do the calibration, I essentially want to remove the connection that I have here and bring that up to the calibration standard. So essentially you want to calibrate out the effect of these cables and everything by doing that. All right. So sometimes that's not possible. maybe because there's a connector difference, or maybe I've got to solder something down to a board, like I may be characterizing a filter. So sometimes it's not possible to do that, and you might have to apply the calibrations in a spot that is not the same place where the DUT connects. But if that interconnect is just simply an extension of the 50 ohm interconnect, you can actually use something called a port extension to say, well, I did the calibration here, but I know the length from here to where my device is. So it can extend that port out to that location. And that's called a port extension. Now, of course, on the NanoVNA, unfortunately, they don't call it port extension, they call it electrical delay. Okay. And the way you can set that up is that once you've done your calibration, you can go into the electrical delay, connect up your DUT, and then oftentimes you can either maybe solder down a little piece of wire or just disconnect right at the DUT to create an open or a short right at the DUT, and then use the Smith chart to actually adjust the electrical delay until you get back to a perfect open or short. I've actually got a video on this, so I won't go into the detail, but that's typically how that would be done. Okay, so you can actually account for the delay difference between where you applied the calibration standard compared to where you're actually connecting up to your DUT. And again, this is really only important when you really have to have an accurate phase measurement. For example, to measure precisely the impedance at the DUT. Again, if you're developing a matching network between stages of an amplifier or a matching network for an antenna or something like that, that's when it's important. If you're just doing an SWR sweep, it doesn't really matter. Don't have to worry about it. Okay. So let's talk about channels and traces. So channels, again, we talked about channel 0 on the VNA are for making the reflection measurements, S11, SWR, input impedance, etc. That's channel 0. Channel 1 is the transmission measurements, okay, insertion, loss, or delay, group delay, things like that, okay. And they're gotten on the menu, through the main menu here, where you can select display. You can then go and select the traces. You can have up to 4 traces active at any time. Those traces can be assigned to any channel, and each one can be on or off. So you might choose, if I just wanted to do an SWR sweep, I would go to display, trace, and turn off all the traces except one. And then with that one trace selected, tell it I want that to be on channel 0. Okay, so now I'm on the reflection channel with one trace. I can do an SWR sweep. So you can pick and choose which traces are on and what channels they're assigned to. So again, common trace formats. We're going to go to display, select a trace, then you go to format. And again, we talked about log magnitude typically for looking at S11 or S21, or maybe an SWR, as another format, or a Smith chart looking at impedance. So excuse me for a second here. So for channel 0 is typically log mag of S11, Smith chart for complex impedance, or linear SWR. For channel 1, the transmission measurements, again, is typically the log magnitude or insertion loss, which will be S21, or phase or delay measurements. So those are the most common ones that you'll have. There are other formats available. If you're kind of into RF design and things like that, some of these might be important to you, but I'm not going to go through them in detail here. But lots of different formats available for you. This transform function that's here is the thing that we use to measure distance to fault or length of a transmission line, for example. So another important thing that you need to know how to do is to set the source, which is setting the measurement frequency range you make your measurements over. And you have a choice of either measuring or setting up by start and stop frequency. For example, if you're sweeping an antenna, oftentimes that's the easiest thing. Okay, I've got a 40-meter antenna. I want to set my start to 7 megahertz, my stop to 7.3, right? Or you can set the center frequency and span. If you're designing a filter, for example, it might be more helpful to say, okay, I know that the center of my filter is 455 kilohertz, and I want to measure a 1 megahertz or a 500 kilohertz span around that, for example. Okay, so it might be more advantageous to set it that way. So it's your choice which way you want to go. If you want to make measurements at one frequency, okay, then you can set CW frequency, and that'll just cause the NanoVNA to output a single frequency and not make a measurement sweep. So there's sometimes that might be important for what you're trying to do. So there are markers available. There's actually up to 4 markers. When you enable a marker, it appears on every active trace that's on the display. Okay. Again, up to 4 markers available. The jog wheel will move the markers back and forth in frequency. Or you can, again, touch your finger on it and drag it back and forth. Okay. The markers are shown on the display up here along the top. So let's kind of look at what this display looks like. So we see the yellow text right here on this first line, channel 0, which we know is the reflection port. When it's displaying log mag, this is the log magnitude of S11 of the reflection coefficient. Okay, so that's what this yellow trace is showing me here. The 10 dB per means that I've got 10 dB per division. The little arrow here means that this is the reference point, so that's 0 dB. Okay. And then the value here is actually the value where the active marker is. The active marker is shown right here as marker number 2. It's sitting at, in this case, at 360 megahertz. And so that means that this point right here is 360 megahertz, okay, going across my frequency range here. And the value of this trace is minus 8.19 dB, okay, at that point, okay. The selected marker again is shown here. That's marker number 2 in this case, with the 2 on it right there. If we add delta markers, the D says that the delta from marker number 1 is 359 megahertz. See, marker 1 is down here, so that's 359.98 megahertz away from marker number 2. All the markers track each other on every trace, so they'll always be at the same frequency, but on each of the traces. There are search features for the markers that allow you to automatically move the marker back and forth, left or right, to find peaks and troughs, to maybe find the minimum, SWR, etc. Okay. And there's also operations you can do with the markers, meaning, let's say I've got a marker I've moved and say, I want that to be my new center frequency for my measurement. You can do a marker to center, and that'll readjust the center frequency of the VNA to be where that marker location is. So that's what the operations do. And then if you're looking at a curve on a Smith chart, you can choose what units the Smith chart is showing. In this case, channel 0, this green trace is a Smith chart trace that's on the circular axis here. And what it's showing, marker number 2 is sitting at 22.8 ohms and 50.1 picofarads right here. That's where that is on the Smith chart. So what's the basic setup process here? How do you actually go use it to do something? So the first 2 steps are configure what traces you want turned on, what channels you want those traces attached to, and what formats you want those traces to be displayed in. And you want to set up the stimulus, the start and stop frequency, or the center and span. Those 2 can be done in either order. It doesn't really matter which one you start with, but those 2 things you want to set up first, and then go ahead and run the user calibration, and then save it. It really doesn't matter, again, what order you do this. And you can even add traces later on, but it's important to kind of do that calibration after you set the stimulus. Then you go off and connect your DUT and make your tests, make your measurements, take a look at what you're doing, etc. You can add markers to kind of get some more numerical results off of those traces, etc. And adjust the traces and formats further if you want to. So that's kind of the general order in which you would go through in using the NanoVNA to make your measurements. So here's a couple of examples of what that looks like. I'm not going to go through the menu structure, but this is kind of what the results look like. So let's say a very common example, I want to sweep and measure an antenna. Okay, I've got my antenna connected to channel 0, which is my S11 port. So there's my antenna right there. And so let's take a look at what we have on the screen. The frequency range we measure over is shown down here. So we set it up through the menus, but it shows up here. In this case, I'm measuring over the 40 meter band. Okay. So this is looking at a dipole antenna that I have set up here, my 40 meter dipole. So this bluish trace right here, to note that color matches this color up here. Okay, that's attached to channel 0, and it's measuring SWR. Okay, and the scale is one per unit here. So essentially I've got 1 to 1, 2 to 1, 3 to 1, 4 to 1, etc. So this is the SWR sweep versus frequency over the 40-meter band for that antenna. My marker, unfortunately, I left it right at the beginning here for this picture, so it isn't at the base place, but we can see that marker number 1, is sitting at 7 megahertz right at the beginning of my sweep, and the SWR at that location is 4.73 to 1, okay, on the bottom end of the CW portion of the band, okay? So obviously this antenna is actually on a tuner, so often, you know, I've got it tuned right now to the phone portion, but I could adjust it to tune to the VSWR portion if I need to. The complex impedance looking into the antenna is shown here by this little curve trace here, and that is using the Smith chart axis, which is these ones with all the circles and arcs. Okay, we can see that again at 7 megahertz, the input impedance looking into the feed line of my antenna and its feed line and the tuner at that frequency is 16.4 ohms, 822 nanohenries. Okay. The reflection coefficient, or the log magnitude of the reflection coefficient, or log magnitude of S11, that's the yellow trace here, okay? And we can see, obviously, its minimum is also going to coincide with the minimum of the SWR. So that's what's being shown there. So that's typical things that you do with an antenna. You may not care about your antenna's actual input impedance. You can actually just turn that trace off. The Smith chart will go away. Once you do that, all those little circular grid lines go away as well. You just wind up with a regular rectangular grid for the other traces. So here's an example of measuring a filter. This is actually measuring a low-pass filter that I designed to go on the output of a Michigan Mighty Mite low-power CW transmitter, 3.58 megahertz. So again, the frequency range is shown down here at the bottom. I made this measurement from 1 megahertz out to 15 megahertz. The insertion loss of the filter, or S21, okay, this S21 parameter is shown here in this blue trace. You can see that's attached to channel 1, so it's making a transmission measurement. The log magnitude response of the insertion loss. So I can see it's all sitting up here at 0 dB at low frequencies, okay, which is where I want it. My fundamental is sitting right about here, okay, of my CW transmitter. Okay, and if we look carefully, if I look at marker number 1 is sitting at about 10.52 megahertz. That's about the third harmonic of my of this transmitter, and I can see that at that third harmonic frequency, the insertion loss of the filter is about 47 dB. So that tells me this filter is going to knock down my third harmonic by 47 dB. Okay. I've also got the SWR looking into the filter, and I can see it's well under 2 to 1 all the way through the passband, which is good. I've also got the reflection coefficient, the log magnitude of the reflection coefficient. And again, because I'm below 2 to 1, I'm also below minus 10 dB of the reflection coefficient over that input passband. And we can see as we go past the corner of the filter, we see kind of what that filter is doing is it's taking all that, any higher frequency energy, and the SWR is rocketing up, the reflection coefficient is rocketing it up. So that means that all those higher frequency components are being reflected off of the input of the filter and not being allowed to transmit through the filter. Okay, so that's how it's rejecting that signal. It's not getting to my antenna because it's being reflected off at the input, being rejected at the door. Now I've also included the input impedance of the on the Smith chart here. Didn't really have to have that to measure the filter, but I had left it on when I took this picture. So if I want to measure coax length, this is where I use that transform function that I mentioned. Changing that channel 0 to linear gives you this sharper peak. And in this case, we can see that sharp peak is occurring about 100 or so, a little more than 100 nanoseconds down from the beginning. Actually, it looks like it's 76 nanoseconds. So 76 nanoseconds down. Now you say, well, how far is that down my coax? It's actually the round trip delay out to the end of the coax and back. But you can actually tell the VNA what the velocity factor of your coax is, and it will then compute the distance for you. So in this case, it tells me that the length of that coax was 9.13 meters, or a little over 20 some odd feet of coax that I'd connected up to here. Now, of course, if I take the other end of the coax, if I've got it available to me and connect it up to the input, I can then also measure the insertion loss, or S21, by turning the transform function off and just changing that to log magnitude on channel 1, and measure the loss of the coax versus frequency, much like the previous example where I measured the characteristics of a low-pass filter. So those are a couple of examples of how you'd use a NanoVNA. And I've got some videos on my YouTube channel kind of showing each of these measurements in a step-by-step process. Now, of course, we talked about at the beginning, one of the reasons we're interested in this is because it's ridiculously inexpensive. And well, as you might imagine, there are some limitations and downsides. So I like to call this the good, the bad, and the ugly about the NanoVNA. So let's talk about what some of those things are. Well, the first one is, again, only 101 trace points. And for a long time, you couldn't adjust that. Again, some external software helps with that. But again, there is some new firmware out there that helps to address that one limitation, but still doesn't come anywhere near what some of the professional units can do. So, but check out some of the other firmwares that are out there. The other thing with the NanoVNA, especially the H versions and the H4, is that the output is not a sine wave. It doesn't look like an RF signal. It's a square wave, okay? And on the H4, it's a square wave at about 600 millivolts peak to peak. This is what it looks like on an oscilloscope, okay? So all the measurements up to 300 megahertz are made essentially on the fundamental of that square wave. And this is what it looks like in the frequency domain. So there's my signal. That's the spectrum of the signal at the fundamental frequency. But when you make the measurements between 300 and 900 megahertz, it uses the third harmonic of that square wave. So it uses this signal here, still the same signal down here. The 900 meg to 1500 meg uses the fifth harmonic. So this is what's being applied. In fact, this display, this 200 megahertz, this is a 200 megahertz square wave. This is the exact same output that you'd get if you're making measurements at 200 meg or 600 meg or 1 gigahertz. It's the exact same output, okay? Because we're just using the different harmonics of that same signal. So you have to think about what kind of device you're measuring, and will it have a problem with the fact that the signal is a square wave and not a sine wave? Will it have a problem with the fact that it's got all this higher order harmonic energy in it? In many cases, it may not matter. In some cases, it might. So if you're testing an amplifier, for example, it might, or a mixer or something like that, it might, okay? So that's something to think about. The SAA2 versions, the V2 versions, still output a square wave, but they use the fundamental for all the measurements. But it still is kind of a square wave looking output, okay? Also, keep in mind that the output power coming from channel 0 is not adjustable on most of the VNAs. There are some out there that do have some adjustability now, but the NanoVNA H4 that I used here, it's not adjustable. So the amount of power in the fundamental from 50K to 300 meg is about 0 dBm, 1 dBm, plus or minus a dB or 2. The third harmonic that's used for 300 to 900 is about 10 dB lower than that. The fifth harmonic is about another 10 dB again, 10 to 12 dB lower than that again, okay? And that's just because of the energy in those harmonic values. So again, is that output power correct for the device you're measuring? For an antenna, for a passive filter, for things like that, you don't care, right? But again, if you're developing an active circuit, like an active filter, an amplifier, something like that, a buffer, then it may matter, and you can't adjust it. Okay? So if you need higher power, you have to throw an amplifier in there. If you need lower power, you have to throw an attenuator in there. So, but because you can adjust the power, you can't make some common RF measurements like gain compression measurements and things like that because you can't adjust the power. Also, the receive power into the reference level, if you will, for the receiver is not adjustable. So what that means is if I'm testing an amplifier, what I need to do is follow that amplifier or have somewhere in the chain an attenuator that's equal to the gain of the amplifier or close to it, so that I don't overdrive the input of the VNA. So because you can't adjust that the receive level, so it just is what it is. And it's got somewhat limited dynamic range. Now I mentioned 60 dB as a number earlier. That's pretty common for some of these NanoVNAs at the fundamental range, 50K to 300 meg. It goes down closer to about 40 dB dynamic range in the third harmonic. And I'd say, well, that's still a pretty big dynamic range, and it is. But compared to professional units, they're typically 110, 120, 130 dB dynamic range. So it doesn't come close to that. You might say, well, I don't really need all that. The thing is, you might. I mean, let's say if you wanted to characterize, say, the duplexer that you might use in a VHF repeater, right? You might want to be able to measure 80, 90, 100 dB of isolation between your transmit receive cavities. Okay, you won't be able to do that with a $50 NanoVNA. Okay. The resolution bandwidth in the measurement is also not adjustable, and there are probably other limitations and things like that as well. But at the end of the day, it's $50, right? So it's pretty amazing what you get for the money. So in summary, I kind of call the NanoVNA kind of the RF tool or toy of the year. A really amazing capability for about $60 US. I mean, if you think about even like a decent graphing antenna analyzer from the likes of MFJ or Array Solutions or Rig Expert or something like that, you're spending 3, 4, 5 times this money for that capability. Okay. Now, are there features that some of those analyzers have that the VNA doesn't have? Yeah. The NanoVNA's display isn't going to work as well in bright sunlight as one of these others, for example. But for this price, it's almost like a no-brainer to get something like this to play with for doing some of this work. There's a ton of videos and things like that that are out there, both on my channel as well as other folks that have published how-to videos on using the VNA for doing a number of different jobs. Really active user groups online that there's a pretty active email list associated. A good US source for these NanoVNAs is R&L Electronics, rnl.com. You just search for NanoVNA and you'll see the various ones that they've got for sale. That's where I got my my H4. So with that, again, thanks for your attention, and I guess we'll unmute the lines and I'll stop sharing here so I can take a look at the chat room to see if there was any questions. Little last minute plug again for my YouTube channel here. So we'll stop sharing here so I can check the chat room. And
I got the questions from the chat room, so we can start that way.
Okay, yeah, that'll work.
Go on.
Yeah.
Want me to go ahead, Dan? Okay.
Yes, go ahead.
First question is, why is the R coupler placed before the A coupler? I would think the A coupler would add a bit of loss to the signal, leaving the VNA, making the measured frequencies signal inaccurate.
So it's a good question. I drew them. I didn't draw them in any particular order for any reason. So it's probably just more convenience in the way that I put them together. The actual construction in a real VNA is got to take those things into account. In the case of the NanoVNA, that's not really an accurate drawing anyway. It's just a simple bridge that's being used. But good question.
Okay. Now, someone also made a comment about to calibrate with my standard SMA connectors. They have to use adapters. And I assume he's asking, do the adapters affect the measurement?
That's another good question. The answer is they can. It depends on what frequency you're running at. The first and foremost thing that you might run across is the delay through the adapter, and that may not matter until you get up to a couple of hundred megahertz. If you're measuring at HF frequencies, it probably doesn't matter at all. Okay, but if you're trying to measure an antenna at 450 megahertz, you might want to account for that adapter using something like a port extension.
Okay, and the SSA stands for Signal Antenna Analyzer?
Could be. I don't know. So, I don't know. We have to look up on the website, see if they define it.
So the VNA will do everything an SWR meter and an antenna analyzer can do, plus more, correct?
Yes, generally. Yep.
Okay. And does this model of the NanoVNA have a USB port to connect to a tablet or a cell phone?
It does. The NanoVNA H and the H4 both have got a USB-C port, and it'll come with a USB cable with a regular USB connector on it. I've only ever connected it to a PC, but I do understand that there are Android applications to use it as well. I just can't comment on them because I've never used them.
Right, okay. If log mag is the same as return loss, then why does the NanoVNA plot this as a negative number? And that was his understanding.
Okay, so good question. So the log mag is, and I might have misstated that it's return loss. It's actually reflection coefficient. Okay, reflection coefficient is essentially always a negative number for a passive device, all right, because it's between 0 and 1. So it's always a number less than 1, which means that if you do the log mag of it, it's a negative number. Return loss is properly quoted as a positive number because it's a loss number. Larger loss is a larger positive number. But the reality is, if you take the log mag of S11, the reflection coefficient, and just remove the negative sign, that's return loss, okay? But so it really is plotting the log mag of S11, so it's a log mag of the reflection coefficient. So if you want return loss, just remove the negative sign.
Okay. Where can the 4-inch HT be purchased? They all seem to be about $95, but I think you mentioned that they are available around $50.
Yeah, so the NanoVNA H4 that I showed here, if you go to RNL Electronics, rndl.com, and you search for this NanoVNA, the H4 with some cables, comes with 2 little cables and a cal kit, was like $59.95 or $64.95. It was in that neighborhood of between $60-$65 last time I checked.
Okay. Is it fairly easy to find and load updated or custom firmware?
It's actually pretty easy. Well, I should say there's a lot out there, but if you follow some of the links off of the wiki page, you'll find you can essentially find files that they're dated and things like that. You can see that's the latest version, and the firmware update process is pretty easy on the H4. I actually just recently did a video on that to show how to do it. And if you don't like it, you can undo it and go back to the firmware you had and that type of thing. So it's a simple matter of downloading a tool, a software updating tool from ST Microelectronics, and then the update process is a simple thing.
Okay. And thanks to Steve, KB8STB, for helping in the chat room, answering some of these questions. Okay. Go on. Is the phase graph the easiest way to find the resonant frequency of a dipole? So resonance is when the phase is at 0 degrees, correct?
Yeah, so resonance is defined by essentially the reactive component going to 0. So in other words, the phase going to 0. Resonance doesn't always mean 50 ohms, right? So for example, if you've got something that's got a 25 ohm impedance or 25 ohm resistance with 0 reactance, that's resonant, but 25 ohms is still going to give you a 2-to-1 SWR. Okay, same thing, like 100 ohms is still going to give you a 2-to-1 SWR, right? It's 0 reactance. So the crossing through 0 does define resonance, but doesn't necessarily define the minimum SWR point.
Okay, this is an interesting one. What happens to S21 if I plug in 2 rubber ducky and 2-meter antennas into port 0 and port 1 and sweep 2 meters? Can I discover the sweet spot of each antenna?
Well, you can discover the mutual sweet spot between the antennas. You won't be able to tell which one is better, but you certainly will see the maximum coupling between those 2 antennas, both in terms of transmitted energy into the first antenna and then the received energy through the second.
Okay. And someone said really good instruction for those of us who are not RF engineers. Thank you. And that's all the questions in chat, Dan. You want to start to take, wait a minute, there's one more. What can a $500 rig expert antenna analyzer do that the NanoVNA cannot do?
Well, the rig expert includes, I like some of the rig experts too. I've got one of the A55 zooms, had it for a while. It's got some convenience features. For example, it can do like a multi-band SWR. Can give you like a multi-band SWR sweep. So if you're trying to tune up a multi-band vertical or something like that, you can look at multiple bands at the same time. And you can say, well, why don't I just set up a wide sweep on the NanoVNA? Well, the problem is, again, you've only got those 101 points. Okay, so you might, those 101 points, you can't determine exactly where they're going to land, all right, but you know, and you're likely not going to be able to put them over every band of interest. Whereas like the multi-band SWR sweep in the Rig Expert will give you single frequency measurements in each of the bands. So you're kind of targeting each of those. So that's handy. It also has, you know, a couple of other features like you can actually report back an SWR through like beeps through like a VHF handy. So you can actually stick the antenna analyzer in one spot and go off somewhere else and make the measurement type of thing. So there's some handy things that are specifically geared towards antenna analyzing that are a little more convenient to use on something like a Rig Expert. And also the display works better in the bright daylight than better than you know, the NanoVNA does in bright daylight. So, but you know, is that worth the 5 times more than it costs? You have to be the judge of that.
Okay. If he uses this in his shack through, say, 120 feet of RG213 to an 80 ohm dipole, should there be just one resonance spot in the dipole where X equals 0 ohms, even if the SWR is not 1-to-1? And that's from K3EUI.
No, Barry, well, not necessarily. I mean, you certainly can spiral around on that Smith chart and have a number of places where you cross the, you know, the prime axis through the Smith chart across a frequency range. So that can happen. And again, like I mentioned, resonance doesn't always mean the lowest SWR. Resonance doesn't mean a 1-to-1 SWR. Okay. So resonance just simply means that's where the reactance went to 0. Okay. So essentially for any given impedance looking into a hunk of coax, if you change the length of coax, you'll rotate around on that Smith chart. So if you plotted any impedance on the Smith chart and you draw a circle that's coincident with the center point, the bullseye, that circle, any point on that circle represents the same SWR. So SWR does not change with coax length. The input impedance looking into the coax length does change, but the SWR does not. If you find that it does change, it probably means you've got some common mode currents on the coax. But if you don't have any common mode currents, there's no change in SWR versus transmission line length. You're just rotating around that chart. You may find that your particular tuning circuit might be able to deal with certain impedance combinations better than others. So that's why sometimes adding or subtracting a little bit of coax makes it easier for your tuner to do its job, because it may be able to accommodate certain impedance combinations better than others.
Okay. Does the NanoVNA have issues when working in a high RF environment, like having an AM station right down the street?
I don't have direct experience with it, but I wouldn't be surprised. It's $50, okay? So you kind of get what you pay for. So I wouldn't be surprised. It does do down conversion, you know, into, you know, through the mixers, you know, to get it to actually make the measurements. But if you overload those mixers, you can get distortion components that go through. So I wouldn't be surprised that you might have some issues with if you got high, you know, a lot of RF energy coming back down the antenna from a strong station. So again, it's a $50 instrument. So
Okay. Can you think of the Smith chart like a dartboard where the bullseye is at 50 ohm R and 0X?
yes, you can. So the Smith chart, if you think about it, the very center of it, well, the very center of it is what we would typically refer to as the system impedance, which most often is 50 ohms. But if you look at a Smith chart, the number associated with that center value is 1. Because what that means is that the Smith chart is normalized. So if you say, I know I'm working in a 50 ohm environment, you take all your impedance measurements, divide them by 50, and that's how you plot them on the chart. But the Smith chart could be used for other system impedances. It could be used for, you know, it was developed actually for 600 ohm impedances for telephone transmission lines. Okay, so the center of the chart was 600 ohms. You could actually have the center of the chart be 75 ohms, or even something that's reactive. Okay, just by normalizing to that component. For our cases, almost all the time, the center of the chart represents 50 ohm resistive. And then the 3 o'clock position is the perfect open, the open circuit position. The 9 o'clock position is the perfect short. And then anything above the middle line represents inductive components. Anything below the line represents capacitive components.
Okay, that seems to be all of the questions in the chat. Dan, do you want to start to have people raise their hands, or?
Yeah, I don't see anybody raising their hands. Down at the bottom of that list, the participants list, is the place to click for raising your hand if you have a question there.
All right. Well, I appreciate it. I'm glad I didn't hear any snoring, so that was good.
No, it was a great presentation.
All right.
Yes. All right. Any comments out there?
Oh, looks like Dale, you got your. Oh, that's a thumbs up, not a raised hand. Okay,
Well,
thank you.
Okay.
it's a comment. It's a comment also.
Okay, sure.
When you get the NanoVNA,
And video and audio.
is it working? I had this before. Key down.
Okay, go ahead.
You're good. Go ahead.
It's good? Okay. Buy a coupler and put that on the NanoVNA terminals to prevent losing that delicate terminal that's attached to the case. Because if you break it at the case, you're looking at the loss of the unit probably.
Yeah.
But that cheap little coupler, yeah, he's got them on there permanently.
Yep. Yeah. So I've got.
Protect it.
Yeah, they call them connector savers. And
Right.
it's really just a male to female, 3.5 millimeter or SMA connector. I've got a box of them and I put them on there. So I make all my connections on here. Not so much if I break this other one, but typically you're going to wear this connector if you use it a lot.
Right.
So you don't want to wear out the connector that's on the unit because then it's done. You wear this out, you take this off, throw it away, put another one on, and you're good to go again. So we call them connector savers.
And are you familiar with NanoSaver, that
Yeah,
software program?
Yeah, NanoSaver is probably the most popular offline PC package to use with the NanoVNA that allows you to, it'll on your PC will separate out the Smith chart and the return loss plots and things, or the plots separately. Instead of having them all laid on top of each other, you can also make measurements over multiple segments to get more measurement points and things like that. So that's what that software package is for.
I've got it, I use it, and I swear by it. It's awesome.
Oh, great.
It made the NanoVNA worth much, much more.
Oh yeah, and like I said, for me, I don't have a computer anywhere near my bench where I'm building stuff. So, what I like about this is it's small, standalone. I don't have to be tethered to a computer. But if you've got a computer there, NanoVNA Saver and other tools like that can be really handy.
Okay.
Thank you, Dale. So I think Mike, NA6MB, and Gail got a question.
I have a very serious question for tonight.
Okay.
You're from Tuland and you are wearing a Mohawk t-shirt.
Yes,
Is
I
that
am.
Mount Mohawk next to Mount Minnewaska, exit 18 on the thruway?
Well, the Mohawk comes from the Mohawk Mountain House.
Yes.
Okay. Yes, that's where the T-shirt's from. My wife and I got married there, so that's where that's from.
Very cool. I went to New Paltz State, so you know.
Okay.
Just,
Well, I know exactly. Run right past it going up there.
Is the question,
thank you.
is the presentation going to be available on your YouTube channel? I know we're going to make it available to everybody. After tomorrow, probably tomorrow morning, Dan will be putting it out.
Well, yeah, I mean, I've done this presentation for probably almost a dozen different clubs over the last couple of months, and most of them have got recordings available. So I don't have one on my channel, but what I can make available is I can send Dan or whoever would need it a PDF copy of the presentation itself, so people can have that and take a look at it and use it, whatever you want to do with it. But then if you've got the recording of this session, you can go back and review that anytime. So
Yeah, that's exactly what happened here. If you'll send us, excuse me, PDF. Boy, timing is horrible here. The PDF, I'll be sending out a link to this video probably by tomorrow morning sometime.
okay, yeah, I'll get it to you tonight, no problem.
Okay, are there any comments out there?
Yeah, just looking through here, a couple of some private comments that were thank yous, and I thank you for sticking around and listen to me gab on here. So certainly appreciate that. So, but yeah, so
Gary wants to know if we can share his screen. Should we let him, Dan?
Who? Yeah, go ahead. You can do it.
Okay, let me find him. I just had him on here.
Yeah, Barry, I just finished watching your video earlier that you had sent me, so. So I guess you're gonna share your Smith chart that you were talking about maybe in your email?
Get him to, can you make,
Yeah,
can
so
you-
far it says host has disabled.
All right, let me see if I can do it.
Dan, can you make him a co-host?
You should be, who is it?
Barry
Oh,
K.
Barry, K3EUI,
All right, let me,
Philadelphia.
let's see. Let me see if I
Oh,
can,
EI, okay, hang on.
let's see.
Okay, Barry, you are now a co-host.
You should be able to share your screen now. Unmute yourself. Here we go.
All right. Okay, so there you go. Okay, so yeah, so this is actually, is this the NanoVNA saver that you used here? I think you're still muted, Barry. Yep, you're still muted there, Barry.
Hold on.
You're still,
Where he
you're,
is. I'll get him unmuted. Okay, he's unmuted. No, he's still muted.
yeah, you're still muted there, Barry.
Push your space bar, Barry.
Yeah, I still got you muted. But yeah, so I think this is the
Okay,
Smith
am I
chart.
live now?
There you go. Now we got you.
Oh, okay. I had to undo the screen share. Let me go back to screen share.
Okay. Well, actually, we still see it up here. So.
Yeah, we
Oh,
still
you
see it
do,
up
I
here.
don't.
Well,
Okay,
yeah, you.
well, here's an 80-meter vertical, and it fooled me because when I looked at the phase, there's two spots.
Yep.
The phase is 0, and one is real sharp.
Mm-hmm.
So I tuned this to the low end of the band for like CW and digital stuff.
Right.
Let me see if I can get my screen share
Well,
back.
Well, what's interesting and what you'll probably find if you look at that Smith chart plot, and this is a good example of it.
Yeah, here we go. I got it.
Yeah. So if you look at the Smith chart plot, the where you cross through the the prime axis in the center, you've got one near marker number 2 and near marker number 3. They're not exactly at those points, but that's kind of where they are, right?
Yes,
And
and that fooled me.
Yep, and that's okay. But also what you'll notice too, or what and you'll notice that neither of them correspond to the minimum SWR.
Right.
Because the way to, on a Smith chart, the way to visualize the SWR is you visualize the distance of the trace from the very center. So if you put the very center and you drew a line to how close does that trace get to the center?
Yeah, real close because
it
the
gets
SWR
close.
is like 1.2 or something.
Yeah, so it gets really close, but it's somewhere between your markers 2 and 3.
Yes.
Okay, so that's telling you that the minimum SWR is not occurring at the resonant points
Correct.
of this antenna system.
Correct.
So, and that's exactly true, and you can see that in the combination of your plots as well as on the Smith
Yeah,
chart
so
itself.
if you look at the phase plot, the S11 phase on the far right here.
Yep.
Here's
Yep.
2.
Yep.
Okay. And then just beyond 3, look at this. That's what confused me.
Yeah. Well, that's essentially
there's a real sharp rise.
Yeah, what that
So
is it's essentially a wrap because
Okay.
you have to think about plus 180 degrees and minus 180 degrees are exactly the same point,
Yes.
right? It's just an inversion. So if you pictured it, if you slid this upper part of that trace down, the part that's to the right, if you
Yes.
slid that all the way down that straight line and connected it up at the bottom, you'd see that would be a nice smooth curve.
Yes. So this
Okay.
is implying there's 2 resonant frequencies on one. The vertical is actually like about 40 feet of aluminum tubing with a loading coil at the base and a little matching unit.
Yep.
And then 2 above ground radials that are about 70 feet long.
Yep. Yeah. So there are 2 points that are resonant, meaning 2 points where the phase is 0, but
Yep.
neither of them are at the lowest SWR.
Right. But real close. I mean, it's,
Yeah.
the antenna
they're all
works
really
fantastic at night on 80 meters. I
Yeah,
hear the world.
they're all real close. You know, like I said, if you draw concentric circles around the bullseye,
Right.
those concentric circles are circles of constant SWR.
Yeah.
So you could actually draw one at the 2-to-1 SWR and see all of the places where you're below 2-to-1.
Right.
Okay. So
This nano saver saved my life because when I tried to use the little small display and the 4 colors, and The irony is I'm kind of colorblind, so the yellows and the greens look alike, the blues
Right,
and the
right.
purples look alike. But as soon as I picked up this NanoVNA Saver software, and
Yeah.
I could, see all the graphs separately, and then make the colors whatever I wanted, I
Yeah.
thought, oh, now I understand what's going on.
Yeah, yeah. The other thing too, if you look on the upper left of the display, you got the start and stop frequencies, center
Yeah.
and span, and then below that you have the number of segments.
Yeah, so
And
I
that's
purposely made them a little larger.
yeah, because each segment is 101 points. So by 20
Right.
segments, you've got
Right.
2,000 measurement points in your
And
sweep here. So,
It took about 1 minute to do the whole sweep, but
yep.
then the curves were real pretty with no gaps.
Oh yeah, absolutely. Yep.
Thank you very much for the presentation.
Oh, well, thank you.
I can unshare here.
All right.
Stop share.
Okay, thank you. Is there anybody else out there?
All right. Well, I got some comments, some folks that are just saying thanks, and again, thank you for coming. And a nice comment about my YouTube channel. Again, lots of stuff ranging from ham radio related things, RF topics, test and measurement topics, even some repair videos and things like that I've done. So if you're ever bored on a snowy winter evening, it's something you could do. It'll either entertain you or put you to sleep, one or the other.
We're stuck home because of COVID-19.
There you go. There you go. That's the best thing that's happened to my YouTube channel, I'll tell you.
All right.
I haven't had time to put content on it. I've just had people watching it.
Well, you do a really good job, and you did a great job tonight. There's a question on there for Barry to pop off. Go ahead, Barry. Well, okay. Doug, AB7DQ is asking if NanoSaver software is open source.
I believe it is. I think the source code's available. There's other people out there that have got software as well, so that is open source. Let's see, there's a question above that, where I raised on Forrest Mims, and absolutely, the Forrest Mims Engineer Notebook series was absolutely a big influence on my early career, and in terms of what schematics ought to look like with your hand drawing them. So, again, so there are other software packages out there. That SAA v2 version, there's a separate software package called NanoVNA QT or something like that. Is software that is used with that one. So that's, again, the different versions kind of have different software, but the H and the H4, all use that NanoVNA Saver software, or can use it.
Okay, great. Are there any more questions?
I'll make a quick note that RNL typically buys 10 or 20 of these VNAs at a time. So if even 10% of everybody that came here went off and bought one, you'd probably sell them out. So if you want one, go get it now, or they sell out.
Well, it looks like KQ4L already did that in South Carolina.
Yeah, right. That's what kind of prompted me to think that. So.
Okay, Dave, do you have a question?
Yeah, just a comment. How much have these things changed over the last year and a half? Having worked with high-end network analyzers over the years, I have some very precision loads, and no matter how I calibrate mine with the open and short and loads that they've supplied, or with precision ones that I have, my 1.1 standards do not read 1.1 on my VNA.
Yeah, well, again, it comes down to, I mean, a lot of them, especially the standards, when you get to the professional units, are more than just open short load. That they've got a table of coefficients that get entered into the software to take into account things like fringing capacitance and things like that. The NanoVNA doesn't take care of any of that. Okay, so again, it's the difference between a professional instrument and a $50 hobbyist instrument. What I've found is that some of the new SAA V2 or the NanoVNA V2 plus 4, I've read has actually got up to 90 dB dynamic range, which is starting to approach some of the low end, professional units that are out there. And I would imagine they're going to get to the point where if they're pushing things that hard, they are going to have to start adopting some of the more advanced calibration processes that the professional units do.
Okay, are you done there, Dave?
I'm
Okay.
good. It's this thing reads probably about 30% off. Trying to measure a 1.1 VSWR. So compared to some other units I have a bird scanner and a couple other things as well to look at antennas and loads and whatever. And the one that I happen to get, the VNA that I happen to get about a year and a half ago, does not agree with any of them.
Yeah, I think, well, if you go back a year and a half, there was still a lot of change going on, I think, and there was a lot of people making clones. Some of them are well shielded, some of them weren't. I think that settled down a bit on the H and H4 because they're kind of stabilized and mature a little bit. So that there may be some better performance that you get, because I've actually found some pretty good results. You know, I've got the H4 here, and then I've also got a the Tektronix NanoVNA or the Tektronix USB-based VNA that I showed on one of the early slides. I have one of those since I work for Tektronix. So that's like 120 dB dynamic range. It's a pretty decent little, medium cost VNA. And for, sub 500 megahertz measurements, I found the NanoVNA is actually pretty good. Other than the fact that it's limited in dynamic range, but its accuracy and measurement results for looking at things like filters and SWR are really close to what I get with the professional unit.
I think you're probably right. Probably a lot of changes since I bought this, and I think I'm going to have to go buy another one and try it out and see what's changed.
Okay. All right.
Either go with the SSA or go with the H4.
Yeah.
I'm not sure.
Yeah, the NanoVNA, like I said, the only other difference that I noticed with the NanoVNA V2 is that the guys that are developing the firmware for that still have not added the ability to interpolate the calibration points. So you literally have to calibrate anytime you change frequency, right? With the H and the H4, you should, but you can get away without it if you're making small changes. But if you make any change, even if it's a minor change on those SAA2s, you have to recalibrate. Now, there are some folks that have developed firmware for that will do the interpolation, but the ones that you get from the guys, the developers, don't yet.
I have to take a look at that. And,
yeah.
See
You'll notice that
on.
because you change the center frequency, and if the calibration indicators on the left side of the display just go away, then you know.
Yeah, see, mine doesn't even have those indicators on the left side of the screen.
Oh, okay.
So
well, it could be that.
That's how old it is.
It could be the unit you have. You may be able to update firmware on it and kind of get some of those features back, and maybe some improved calibration routines and such.
I could try that too. I just haven't used it for a while. Been too busy with other things.
Yeah, understood.
All right, we're going kind of long on time, but that's okay. This is a great presentation, some great questions out there. Are there any more questions? Any more?
Barry, you're muted, Barry. Looks like you're trying to say something, but you're muted.
Sorry, a comment that ARRL reviewed this a couple of months ago in QST, just to mention.
Yeah, I think there was a review in QEX also, but I did see something in QST as well.
Okay, but that's everything.
All right.
Okay, we've lost a few, but on the East Coast, it's very, very late. And Puerto Rico.
133 max.
I'm sorry, what'd you say, Barry?
We had about 133 max.
Yes, we did.
Nice.
Unfortunately, because of the time of day when we have to have these, those in the East Coast kind of either fall asleep or peel away at some point. They wait for the video to come out for the rest.
Yeah,
that's okay.
Okay, are there any more comments, questions, answers? All right, I'm not seeing any. If you'll send me that the PDF, I appreciate that, and we'll get working on this thing and send it out to everybody.
All right, sounds good. As we close up here, I'll save a PDF and send it off to you.
Okay, I heard my name.
Yeah, this is Dale. This is for Dave Kelterboard. There are YouTubes on the internet on how to make a hyper accurate 50 ohm load, obviously using very accurate resistors, but they show in detail how to put that little device together.
Good information. Good information. All right. Before we go, is there anything else? Okay. Ken, KM8AM is asking how to get on the email list. Send me an email at my call sign K7REX@ARRL.net, K7REX@ARRL.net, and I'll make sure you get on there. There is another way, and I'll put this on here too. Hang on, let me get my down so I can grab the URL. Come on, go away, come on. Here we are. Properties. Okay, and I'll send this out there. I'm plugging in the groups IO for SEC Aries, and that is it's primarily Aries and disaster communications group. And they, if you get on there, there's over 1,000 people in there right now. And if you get on there, you get all the documentations and notices and all that. Is there anything else? Okay, I am going to close this out. I want to thank everybody for coming. And somebody's already jumping on the groups IO, and I'll say 73 is everyone.
All right.
Yeah.
Again, 7-3. Thanks again for everybody attending, and I'm glad you enjoyed it. Thank you.
Thank you.
73 is all.
Good night, everybody.